Moon rocks harbor considerable evidence indicating that the Sun was particularly active during the last ice age. The Moon has no atmosphere. As a result, cosmic micrometeorites, these are dust particles that are traveling very rapidly, along with solar flare cosmic rays, are able to reach the Moon's surface unimpeded and etch permanent records of their arrival in the lunar rocks. A number of these rocks were collected on the Apollo missions and brought back for storage at the Johnson Space Center repository. Careful microscope studies of the rocks revealed that their surfaces were literally covered with tiny micrometeorite craters whose glassy surfaces were finely etched with solar flare particle tracks. By studying these craters and their cosmic ray tracks, NASA scientist Herbert Zook and his colleagues were able to construct a record of solar activity dating back over the past 16,000 years. Surprisingly, what they found was in the earliest part of this record, the solar flare tracks were accumulating 50 times faster than they are today. This dropped about fivefold by 11,000 years ago, at the time the Ice Age came to a close.
NASA scientist, physicist Herbert Zook and two of his colleagues were able to construct a record of solar flare activity dating back over the past 16,000 years. What they found adds further credence to La Violette's theories.
One of the first things that scientists did when they got to the Moon was look for evidence of solar activity changes in the past. And so they measured radioactive nuclei. They were created in lunar rocks from the solar protons, high-energy protons from solar cosmic rays, solar flares, and eruptive prominences. And they were rather disappointed to find that from the aluminum-26 and manganese-53 long half-life data, with averaging over 1 million years, that the activity looked about like it does at present. Didn't seem like solar cosmic ray activity was changing very much. But there was some carbon-14 data that indicated, yeah, you know, carbon-14 is kind of high. It has a short history of several thousand years. It looks like over the last 10 to 20,000 years, maybe something did happen that was increased. The solar cosmic rays, the heavy ions in the solar cosmic rays, also create damage tracks in lunar rocks. These accumulate with time. So the longer rock has been exposed on the surface, the more damage tracks it has. And we can actually etch these, measure the density of them, tell how long that rock has been there. But you need another chronometer. You need something else to measure time with. And so what I did was use meteoroid impact craters as a measurement of time. I also looked personally at spacecraft windows that were returned from space and counted impact craters on there. And you had various kinds of divots on these windows that were caused by polishing or stuff like that. But meteoroid impact craters had these nice melt line pits from the hypervelocity of impact that actually remelted the glass. And I got a cratering rate from that. And the neat thing about the window glass from the spacecraft is that those pits look very much like pits on lunar rocks. So the comparison could be done very easily. My conclusion is that there's rather good evidence that the Sun was more active, possibly much more active, 10 to 20,000 years ago.
Indeed, the increased solar radiation flux associated with this elevated solar cosmic ray activity would have been sufficient to cause the melting of the ice sheets. In graphing their solar flare intensity, the NASA researchers made the assumption that micrometeorite cratering on the Moon's surface has remained constant for the past 16,000 years. However, if cosmic dust was coming into the solar system in large amounts at the end of the Ice Age, this would have caused this peak of solar cosmic ray activity to move to a more recent date and increase in height. Most likely it would have peaked between 14 to 15,000 years ago, which coincides with a time when the Earth's climate globally was unusually warm and the ice sheets were receding at an all-time high. Well, a prolonged period of cosmic dust and gas inflow would have explained the Sun's increased luminosity and flaring. And we can imagine that as this dust was coming in, the Sun's activity was continually building up as this dust was falling to the Sun, energizing the Sun. The corona was becoming more and more active, and these coronal mass ejections were happening now continuously. and throwing off the balls of plasma far larger than we see today. In a matter of days, as it raced towards the Earth and Moon, this bubble of hot coronal gas and plasma would have expanded to form a dome-shaped front, tens of millions of miles in diameter. Upon arriving, this sphere of hot, fiery plasma would have temporarily engulfed the Earth and Moon, producing temperatures hot enough to melt dust particles on the surfaces of lunar rocks. It also would have severely disturbed the Earth's geomagnetic field. In fact, paleomagnetic studies have shown that at about that time, 14,200 years ago, the Earth's magnetic pole flipped to an equatorial location, and throughout this period, the magnetic field was severely disturbed. This would have been caused by the solar flare particles getting trapped in the radiation belts and producing a magnetic field opposed to the Earth's field.
Like the Moon, Earth also preserves a record of rapid heating of its surface. Some of these records are the myths that are held by people from all cultures on the planet.